Hey, so I'm back and welcome to my channel. So, in today's video, I'm going to what's this? Yeah, figure out the exponential of the Pauli matrices. Especially these these three fellows over here. We already know, okay, probably some of us don't know that Pauli matrix of the first one, the sigma naught, oh my goodness, sigma 0 is, well, the identity matrix. So exponential of this thing, well, we can figure out the exponential of this thing, but instead of just figuring out this fella here, how about we figure out these three things, or at least the first two, and you'll get the gist of how to figure out the first one, because they're very similar, and if you can get the gist of the first one, then the rest will be very easy. Yeah, so uh, there are two ways of dealing with this guy over here. Well, technically three ways. First is the traditional method, then we have the similarity matrix or similarity transformation, and then we have the unitary transformation. Although I would call it two methods because similarity and unitary matrices are kind of similar for hermitian matrices. Like, well, they're the same thing technically. So all of these are technically hermitian matrices, and maybe I kind of forgot, but as far as I know, they are. Acha, wait. So let's just are they really hermitian? No, let's just figure it out whether they are hermitian or not. So for this guy over here, um, transformation, the complex conjugate, yeah, this is a Hermitian. This is also an Hermitian. This, yeah. So all of these are Hermitian. Sorry about that. I got sidetracked, but you get the point. So in today's video, we're gonna be dealing with the first method, the god dang it, my handwriting sucks. The traditional method. Yeah. God dang it. Doesn't matter. Fuck it. So let's deal with this crap. I shouldn't say this because demonetization. And not that I really give a crap. So we have three guys over here. So let's figure out the first one, this guy. But first, what is the exponential? Like, what's the Taylor expansion of an exponential, like ex? So for ex, where x is a normal value or variable, our typical Taylor expansion is 1 plus x plus 1 by 2 2 factorial x square. Oh my goodness. I should have practiced a bit. I should have practiced a little bit with my pen, but you get the point. So this is our exponential Taylor expansion. Cool. So how can we turn this guy over here to something that requires matrices? Well, it's the same thing. So for example, if we have a matrix A, this will give us the identity matrix, then we have A matrix itself, then 1 by 2 factorial, then A square, yada yada yada, cool. So that's good, that's fine and dandy. Also, let's not forget if A is, let's say, A, B, C, D, oh my goodness, D, then A square is definitely A square, B square, really though. Um, okay, look, no, let's see. A and B. Oh god, no. This only applies for identity matrices, or not identity, diagonal matrices. Yeah. So if we have a diagonal A, 0, 0, and B, then A times A, so this is A square, and this is 0, this is 0, this is B square. Looks just about right to me. Cool. So, sorry about that. That was just something else. So what do we have here? We have this fella right here. So how do we turn this thing, oh god, into our sigma? Is it big? Oh god, no. Yeah, go. So let's deal with the first one, which is exponential of sigma 1. So this will obviously give us identity. Then we have this. Then we have 1 by 2 factorial this plus yada yada yada. Cool. So that happens. And for just in case, let's not forget that this is a thing. So we'll use it later on, but let's just know this is a thing. Awesome. So what do? What we do is we just do something tricky. Okay, not tricky. It's simple. So here's a fun fact about Pauli matrices. God dang it. Cool. So for example, we have Pauli matrix sigma 1. And this is 0, 1, 0. Oh god, no. 1, 0. So what's sigma square? Let's find it out. Woohoo. Woohoo. God dang it. So this will give us 0, 0. So this is 1. Then this row in this column gives us 0. This gives us 0. God dang it. And this row and this column gives us 1. So this is an identity matrix. And this goes on for all of the Pauli matrices. Oh god, no. God, no, not plus. Let's not get into that. We'll never get into that, probably. Oh, no. Oh god, no. Go. So, yeah, this thing happens. So, with this beautiful fella here, we can say that this guy is I plus sigma 1 plus 1 by 2 factorial I plus 1 by 3 factorial sigma 1. And why sigma 1? Because anything, if you multiply this matrix, if you multiply any identity with A or a matrix, then it gives us a matrix. Another handy little thing, and we'll need a lot of them. So, yeah, that's a good line. Anyway, yeah, we're just about there. Now, for simplicity, let's bring out all the i's to one side. So, I plus 2 factorial I plus 1 by 4 factorial I plus yada yada yada, and sigma 1 plus 1 by 3 factorial sigma 2 plus yada yada yada. Cool. Awesome. Now that what we have here is a good stuff. Some good stuff over here, and then what do we do with them? Simple. We write down the matrices themselves, because why not? Identity, and then we have this fella over here. Now then what? I don't know why I'm making up weird accents, but yeah. I don't even know what my real accent is, god dang it. Sometimes I say something like, let's not get into that. Let's not get into that, okay? No, let's not. Anyway, Now we have sigma, which is 0, 1, 0, 1. Oh god, no, 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 no. Plus 3 factorial. This, this, this. Plus, plus, plus. Now, finally, we can add up all of these things over here and end up with 1 plus 1 by 2 factorial plus yada yada yada, but we know that, well, just for intended purpose sake, let's go for this. Great handwriting, Josh. Nothing less can be expected from you, piece of crap. Anyway, cool. So this gives us all of this. Oh, God, no. Oh, I was supposed to use. Sorry about it. I was supposed to use a projector thing, but something else happened, and god dang it. Yeah, cool. This is 0. Same for here. 1 plus 1 by 3 factorial plus 4, 1 by 4 factorial, and god dang it. 1 by 4 factorial plus this. Cool. Plus, since I don't have any space, I'm just gonna write this thing over here, this fella here. Cool. So this gives us 0. Great. Yeah, so then this stuff, okay, what happened? Right. So this, oh fuck, my project, okay, yeah. So this thing gives us 0, then, oh god, 1 plus 3, okay, 1 by 3 factorial plus yada yada yada, and also at the bottom left corner we have this and 0. Awesome. So what does that give us? Pretty simple actually. So if we add these people here, what we get is, well, let's just write them down here because explaining it is gonna be a bit tricky. So plus 1 by 5 factorial, yada yada yada. What am I doing? Okay, cool. Plus, oh god, 1 plus 1 by 3 factorial plus this, and 1 plus 2 factorial plus, oh no, not 2 factorial, definitely not 2 factorial, 1 by 2 factorial plus this. And you'd be surprised to know what they actually mean. Now, you could do two things from here. You see, these, oh fuck, yeah, cool. You see, you're not dealing with the average exponential anymore. You see, these Taylor expansions has risen beyond your average normal Taylor expansion. Okay, that's not the good reference. For all you DBZ abridged people out there, you got the reference. Of course you did. Anyway, let's move on. So, you will know that our typical cos, oh no, oh god no, cos x is, what is it again? 1 minus 1 by 3 factorial plus 1 by 5 factorial. Damn, go. So this is our cos, and this is our sine, which is x. Okay, this is not x. Okay, this is cos 1. This is cos 1, sine 1. So sine 1 gives us 1 minus 1 by 2 factorial plus 1 by 4 factorial, and this goes on and on. Okay, but here this is definitely a problem. You see, these four things, none of them have any minus sign. So that should tell you that this is not your average Taylor expansion. God, I love the reference. Anyway, so what should we do here? As it turns out, I found out something that is weird. Okay, not me, but like my friend. He's a great guy. Okay, so what he told me was that there are hyperbolic stuff of this stuff. I mean, I already knew, but like I did not know the expansions and the expansions of cos hyperbola, and which sounds like gosh. Of course they do. Which version? So this is actually this. Okay. Oh my goodness, dudes! Did I just mess up the? Ah no, God dang it. Okay, actually, like God, damn it. Yeah. So I even forgot the expansions of these two simple stuff. God dang it. Fuck. Anyway, so cosh of 1 gives us this thing, and sine of h, or sine h of this, but we cannot call it sine h, we have to call it shine. That's right. This is not your average. Okay, I went over this a lot, okay, but you get the point. Great. Livid. I feel absolutely livid right now. I am absolutely livid at this point. Okay? So, these expansions, we know what they are. This is cosh of 1. This is sine of 1. This is sine of 1. Cosh of 1. And we could just end it right here. Definitely we could. But we won't. Why? Because I'm a piece of trash. And I want to take this an extra step further and make it look like a very neat looking crap. Okay? So we also know something about these things, that sine of h, a sine of 1 is 1 by 2 e power 1 minus e power minus 1, and cosh of 1 is 1 by 2 times half of e power 1 and e power minus 1. Cool. So using these things over here, we can write half and e power this, oh god, e minus this, e plus e power minus 1, and e minus e power minus 1. Absolutely amazing. And this is our exponential of first sigma. Cool. Now you know how to deal with such things. And yeah. Oh, by the way, I did write something over here, but we'll not go into that right now. Since I want to increase my watch time for all of you people out there, I'm going to do another one, the second one. So the second one, if you don't know already, or if you forgot already, is 0, minus 1, minus I and 0. So we know this is the case. Cool. So how do you deal with this? We already know the basics, okay? And the basic formula is actually this one right here. So whatever you do here, okay, we end up with this we end up with these fellas right here. So you know the drill, people. You know the drill. That means E equals to exponential of sigma 2 is yours truly E plus E minus 1. Here I times E minus E power minus 1, and here minus I times E plus E minus, oh god no, E minus E power 1 minus 1 minus E power minus 1. Great. And finally we have this. Oh no, oh god no, oh fuck. Yeah, sorry about that. So over here this is minus, over here this is plus. God, dear god. Yeah, I'm not gonna edit it out, okay? I'm not gonna do that. So who cares? You know, plus minus stuff happens. Great. So this is our final one, and you can use it everywhere, every Pauli matrix ever. So here previously I've written this parts over here that includes what we should be doing in the most generalized case of Pauli matrices. Now you see, for any typical exponential of Pauli matrices, we have this stuff here. We have this formula right here. So from here we can generalize it and write down Josh of 1 and Sine of 1 for I and sigma n respectively. Finally, from here we can write the value of Josh, which is this, and Sine of 1, which is this, and we end up with a generalized form of a Pauli matrix exponential. So for any of the stuff, you can just use this formula right here, and voila, you will have your answer 100% of the time. Okay, if you can't, just hit me up. I will delete this video and make another video saying that I was wrong, or I'll make a video saying I was wrong. Of course, no one is watching this video, so it doesn't matter anyway. Cool. So yeah, thank you for watching this video. If you're still here, if you're still here though, then if you haven't subscribed to my channel already, then I'm pretty sure you want to. And if you don't, please do subscribe to my channel, because you cannot miss out the second part of this video where I talk about, or I solve this same problem but using another method, which is similarity matrices or similarity transformation, aka unitary transformation. And of course those are important, very important. I cannot stress this enough, but unitary transformation is very important for linear algebra and finally QM. So of course that's why I'm gonna use that technique in the next video. So stay tuned, and if you have any questions, then comment down below and ask it right away, because I love to answer questions and help out people because I'm a good guy. No, I'm not. Anyway, so yeah, and give this video a like if you like what you see, and again subscribe to my channel, and I'll see you guys in the next video. Peace out. Goodbye.